Hello, am I audible? Okay. So, hello everyone. Welcome you all to live session 2 of NPTEL course Fluid Flow Operations taught by Professor Subrita Kumar Majumdar. And my name is Nagvan Sai Kumar. I am going to be teaching assistant for this course. So, let's have a brief recap of what we have learned in the last week. So, we have learned about fluid flow operations, a brief history, and all the significant milestones that were achieved in the past. And we also learned about important fluid flow properties as well, which will influence the fluid flow. And this week we'll be learning about fluid statics. In fact, the course has already been completed by Professor. Okay, so we'll try to have a recap of all the concepts that were taught in the class, and then we'll move on to the question session. Okay. So, but what is fluid statics? Fluid statics is concerned about the balance of forces when which stabilizes fluids at rest. Okay, when the fluid is at rest, so it will be covering all the forces which acts on these fluids, and it will be talking about the stabilization of this fluid which is at rest. And in case of liquid, the pressure, if you take two different containers of different heights, okay, or let's say of same height, and let's say both dimensions are same, and if you fill this with let's say 5 meters till 5 meters, and this is still 10 meters of identical liquids,
Your voice is
in
not
that case
audible,
you will be experiencing
sir.
more pressure in this case at the bottom. Okay, because pressure is directly proportional to height. Whenever the pressure increases, sorry, whenever the height of the liquid increases, the pressure will also be increasing. Okay, so in case of any liquid, as the pressure largely changes according to its height, it is necessary to take its depth into account. Okay, and whenever the fluid is at rest, there will be no motion of the fluid, right? Okay, so let's say these are two different let's take this, let's say this is a liquid, and let's consider two different layers of this liquid. Okay, so if you consider these two layers, okay, as a entire fluid or the overall fluid is at rest, both these layers will also be at rest, right? So when two different layers or two different fluid particles are at rest, when two different particles are at rest, then there will be no relative motion between these two particles, right? So if there is no relative force or relative moment among these particles, then shear stress will also be zero between these layers or particles. Okay, and the only stress which is involved in the fluid statics is the normal pressure, which is nothing but the pressure force. Okay, so how do or what are the different type of pressures that exist in a fluid? Okay, so we just learned that there is only one type of normal stress which acts in a fluid, right, which is at rest. So that is pressure. So how do you measure this pressure, or what are the different type of pressures that we have, and what are different equipments that can be used for measuring this particular parameter, that is pressure? So let's find out. So initially, let's try to classify the pressure into different types. So yeah, but before that, basically in a fluid which is at rest, it can experience two forces, that is uniform pressure and a non-uniform pressure. Okay, so when a uniform force acts on a plate of let's say area A, so let's take a plate or any surface. Let's say this is having an area of A. So whenever a normal force, this should be 90 degrees. Okay, whenever a normal force acts on acts on a plate of area, let's say A, and then the pressure acting on that particular plate is calculated using formula P is equal to F by A, which we already know. Okay, So in this case, P is the pressure and F will be the pressure force. Okay, and similarly we also have non-uniform pressure as well. Okay, so definition remains the same. Whenever whenever the force acting on the plate is not uniform, that means it keeps on changing, right? So then pressure will also be non-uniform pressure. And how do you calculate this non-uniform pressure? It is by taking a limit. Limit delta A tends to 0, del P by del A, or del F by del A. Okay. So in this case, del F is a non-uniform pressure. Okay. So this will be dF by dA. Okay. So we generally have two type of pressures, and be it uniform or non-uniform, pressure will be having same units, right? So be it uniform pressure or non-uniform pressure will be having units, right? So we generally express pressure in terms of pascals. That is, PA is a shorthand representation of pascals. So pressure also has many other units, be it MKS, CGS. Apart from this, there are also other non-conventional units as well. So we can express pressure in terms of bars. Okay, you can also express it in terms of torr, which is again another unit, and we can express in terms of HG, that is height of a mercury column. So we you will be coming. You must have already known about barometer, right? So whenever you are measuring atmospheric pressure, you will be taking mercury in a bowl, and you know this arrangement, right? You will be taking test tube as well, and depending upon the level of mercury, you will be finding out the atmospheric pressure, right? Okay, so that is why people started expressing pressure in terms of mmHg as well. Okay, this is one unit, and we also measure it in terms of meters of water. Okay, meters of water column. And then we also have atmospheric ATM, that is atmospheric pressure. Okay, so these are different type of units that we can use to express pressure. Okay, so when you're expressing in different terms, there will be relation as well, right, between these units. So we basically express in terms of 1 atmosphere. 1 atmosphere is a standard atmospheric pressure. Okay, so 1 atmospheric pressure will be equal to 760 mm of Hg. Okay, and this should be equal to 101325 pascals. Okay, and if you do it in kilopascals, it will be 101.3 kilopascals. Okay, and then this is approximately equal to 1 bar. So it will be like somewhat approximately, not exactly equal to. This will be approximately equal to 1 bar as well. Okay, and coming to 1 pascal, 1 pascal is nothing but 1 Newton per meter square. Okay, so this is about units of pressure. And then when you are measuring the quantity pressure, it can be expressed in terms of it can be expressed using two different methods. One, let's say you have pressure, you want to measure pressure at a particular location. Okay, so this pressure can be expressed in two ways. One is with respect to perfect vacuum, based on the perfect vacuum, and then it can also be expressed in terms of atmospheric pressure. Okay, so if you measure it in terms of perfect vacuum, then it is called absolute pressure. Okay, and in the second case, when you express it in terms of atmospheric pressure, it is also called as gauge pressure. Gauge pressure. Okay. So let's take an example. Let's say you're expressing, you want to let's say this is a reference level, or you can also call it as absolute zero pressure. Okay. Absolute zero pressure or perfect vacuum. Okay. So this is going to be a reference line, and okay, this is going to be a reference line, and this let's say this is a atmospheric pressure, 1 atmosphere, and let's say the quantity which we measured is having a pressure of 2 atmospheres, and these 2 atmospheres, if it is measured from absolute zero, this is called absolute pressure. If you measure it from perfect vacuum, it is called absolute pressure. But if you calculate this with respect to the atmospheric pressure, this is going to be gauge pressure. Okay, and this can also be in the opposite way, like let's say this is below atmospheric pressure, let's say somewhere here, and this is for example having uh, 0.5 atmospheres. Okay, this was measured with respect to perfect vacuum. With respect to perfect vacuum, this is having a pressure of 0.5 atmospheres, and this is called negative gauge pressure. Sorry, this is also absolute pressure, and this difference will be gauge pressure, or with respect to atmospheric pressure, and this is be a negative value, negative gauge pressure. Okay, so this is how you'll be measuring pressure at different locations. You can either express it in terms of perfect vacuum, that is going to be absolute reading or absolute pressure, and if you measure the value with respect to atmospheric conditions, then it is going to be giving you gauge pressure. Okay, and now coming to the characteristics of pressure. So pressure has 3 main characteristics. The first one is pressure of a pressure of a fluid always acts perpendicular to the wall in contact with the fluid. So let's say you have a container, and let's say you are filling this with some liquid, say water. Okay, so the pressure inside this fluid will always be perpendicular to the wall or the container. Okay, so this never acts at an angle. So this will be always perpendicular, will be acting always perpendicular to the container. Even if this container is at an angle, even if the container is at an angle, the pressure will be always perpendicular to the container. It will be always acting perpendicular to the container. Okay, and coming to the second property, the values of pressure acting at any point in a fluid at rest are equal regardless of its direction. Okay, so there's a lengthy proof that was discussed in the class, so we'll go to the proof as well. So let's consider liquid. let's consider liquid of volume, say dV, which is equal to dx dy dz by 2. Okay, this is the average volume. Okay, so this is going to our x-axis and y-axis. So if you take the front view from this direction, okay, this looks like a right angle triangle, right? So weight of the particle will be, or weight of this sample will be in the downward direction. It will be rho g into dv. There is the volume of the sample, or the volume of the drop under consideration. Okay. So there will be different forces acting along each direction, right? As I've told you, pressure or pressure is considered as the perpendicular force acting on the surface, right? So we will be having pressure in this direction, and in this direction as well. Okay. So let's say the pressure acting on this side, or on this side of this triangle be px. So then its corresponding pressure, force is going to be pressure into area, that is dy into dz. Okay, and this direction, let's say py is the pressure acting along y direction. So the corresponding area will be dx into dz. Okay, and similarly here it will be p into ds into dx. Okay, let's say this is side ds. Okay, and let's say if this is making an angle of beta, let's resolve the components. So this can have a vertical component and also horizontal component, right? So let's balance forces in the x direction. So sigma fx is going to be m into ax. Okay, where a is the acceleration of the body, or acceleration of this particular triangular prism. Okay, so this fa is going to be px into dy into dz minus, okay, this is the first component, and this is going to be the second component. So that will be p into ds into dz into sine beta, right? This component sine beta, and this should be equal to mass into acceleration of the body. So if you, mass is going to be again density into volume, right? So that is going to be density into volume, that is dx into dy into dz by 2 into ax, that is acceleration of the body. And similarly you can also take, will also be balancing forces in y direction, that is m into ay. So this is going to be py into dx into dz, that is this particular force, minus the component, y component of this force, that is p into ds into dz into cos beta. Okay, and apart from this there is also one more force which is acting here, that is minus weight of this sample, that is rho g into dx into dy into dz by 2. This is going to be rho into dx into dy into dz by 2 into ax. Okay, so here this is dy, this is dx, right? So here you can say that dy is equal to ds into sine beta, right? This is ds, dx and dy, dy and dx. So from geometry, and also dx can be written as ds into cos beta. Okay, let's say this is equation 1, 2, 3 and 4. So if you integrate the weight volume of this triangular prism, okay, and then finally substitute it in these equations. Okay. Yeah. Sorry. As the weight of this particular prism, triangular prism, is negligible. Okay. So it can be completely omitted, and you can write equation 1 and 2 as px minus p is equal to rho into dx by 2 into ax. This is going to be equation 5, and similarly this equation can be written as py minus p is equal to rho into dy by 2 into ay plus g. This is going to be equation 6. So if you compare equation 5 and 6, you can say that px is equal to py is equal to p, and also px is equal to pz is equal to p. If you compare it, if you also take z components and then do the same thing, you will be getting this as well. Let's say this is equation 7. Okay, so that means forces, the value of pressure acting at any point in a fluid at rest will be equal regardless of its direction. So px will be equal to py is equal to pz. And coming to the third property, that is the fluid pressure applied. Just a second. The fluid pressure applied to a fluid in a closed vessel is transmitted to all parts at the same pressure value as that applied. Okay. So this is also called famously called as Pascal's law, and this will be used in hydraulics as well. Okay. So if you observed hydraulic press, okay, hydraulic press uses the same principle. So let's say we have an hydraulic press of two different diameters. Okay. Let's say F1 is acting on this platform. Let's say there is a platform here, and then a platform here as well. Okay. So let's say F1 is acting on this platform, and there's a force F2 acting on this platform. Let's say this is having an area of A1 and this is having area of A2. Okay. So when the small piston of area A1 is acted upon by force F1, then the liquid pressure, which will be equal to F1 by A1, F1 by A1. This is the pressure that is produced in the liquid, and this pressure will be acted upon in the second or large piston. Okay. So now F2 will be equal to P, because same pressure should be acting here as well, right? So here P, again it will be F2 by A2. Okay. So if you equate 1 and 2, because same pressure is acting on the same on both the pistons, right? So pressure has to be same, because this is continuous fluid, pressure has to be same. Okay. Now F1 by A1 will be equal to F2 by A2. So this gives us F1 is equal to, or F2 is equal to F1 into A2 by A1. Okay. So this means if you apply a small amount of force here, okay, let's take in terms of numericals as well. So let's say A1 is 2, A2 is having around 16, and you're applying force of 1 Newton. Okay. So you're applying 1 Newton of force on a plate which is having 2 meter square area. So what is the force that is going to be produced on the other end? So let's find out. F2 will be equal to F1 from this equation. F2 is equal to F1 into A2 by A1. So now F1 is 1 and A2 is 16 by A1 is 2. So if you cancel out, it will be 8 newtons. So you are only using 1 newton of force to produce a force of around 8 newton. Okay. So the same principle is using hydraulic press as well to generate larger forces using small forces. Okay. So now coming to the pressure of a fluid at rest, let's take an example of a fluid, or let's consider, let's say this is the surface of the fluid. So here only atmospheric pressure will be acting, right? And let's say this is the depth of the fluid. Okay. So we are considering a particle at a height of around, let's say this distance is h, and the depth of the fluid is around z, and this entire height is, or depth is, z naught. Okay. So if you are considering a particle at this location, what are the different forces acting on this particular uh, liquid? Okay, that is under consideration, and what would be the pressure acting on that particular liquid particle? So let's take in, let's consider this. So let's say this is in the shape of cylinder. Okay. So what are the different forces that are acting? They will be having vertical force, and you will also be having horizontal forces as well. But horizontal forces, they cancel out. Okay. But as there is a change in height, pressure is not going to be cancelling out. But when you consider horizontal forces, they're at equal height, right? So they get cancelled out. But when you're considering vertical forces, they're not at equal height, so that is why they will not be cancelling out. So let's say from the bottom, it is expressing a force of P, and from the top it will be experiencing a force of P plus dP by dz into dz. Okay. Or let's say it is experiencing a force of P plus dP. Okay. So obviously this droplet will also be having a weight, right? Certain weight, that is dW. So dW will be equal to, is equal to mg, right? W is equal to mg, right? So in this case dW will be equal to, and again mass can be written as volume into density, right? So it will be density into, again volume can be written as area into its height. Okay, let's say dz is the height of this particular sample. So that will be density into volume into g. Okay. Yeah. So yeah, for this one small thing, this area is going to be dA again. Okay, as we are considering a small strip. So this area is dA and height is dz. Okay, this is going to be the weight of this sample. Okay. So now let's balance out all the forces. So horizontal forces will get cancelled out, and coming to vertical forces, so let's take this as a positive direction. So that will be P into dA will be one force acting in the upward direction, minus what are the forces acting in the downward direction? P plus dP by dz into dz into dA. Okay, again pressure into area, that is force. Again minus weight of the sample is also acting in the downward direction, right? So it will be rho into g into dA into dz. So summation of all the forces should be equal to 0 if this particular liquid droplet is at stable condition. Then sum of all the forces should be equal to 0, right? If this is at stable condition, or if it is at rest. So let's cancel out all the terms. This gets cancelled out, or let's expand it first. So it will be P into dA minus P into dA minus dP into dA minus rho g dA into dz is equal to 0. So now this gets cancelled out. Okay, and we are left with dP by dz is equal to rho into g minus rho into g. Okay, so I'll take this to the other side. That will be dP is equal to minus rho g into dz. So I'll integrate this. Okay, so if you integrate this, we'll be getting P is equal to minus rho g z plus c. Okay, where c is the integration constant. So how do you find integration constant? So at a value of z is equal to 0, what is the value of P? It will be atmospheric pressure, right? So using that condition you can calculate the value of C. Okay, or sorry, H will be 0, right? Here H will be 0, but whereas value of Z will be equal to this entire distance, okay, or Z naught. So at Z is equal to Z naught, P is equal to P naught, that is atmospheric pressure. Okay, so if you substitute that, you will be getting P is equal to P naught plus Z naught minus Z into rho G, or you can also write this as P is equal to P naught plus rho G H. Okay, because essentially Z naught minus Z will be equal to height of this height of the liquid, right? So you can write Z naught minus Z as H. Okay, so this is how you calculate pressure inside a pressure of a liquid at certain depth. Okay, so that will be pressure at certain height H will be equal to atmospheric pressure plus rho G H. Okay, and this is for liquids, but gas also comes under fluid, right? So it is also fluid, right? So we need to also understand how pressure changes in case of gases as well. Okay, so in case of gases, density is also function of pressure, right? In case of gases, so as the height changes or altitude changes, temperature will also be changing. Okay, because of which density will be changing. Sorry. Okay, so for this is generalized equation for any type of gas, PV power n is equal to constant. For ideal gases, n will be equal to 1. Okay, so at sea level, that is at z is equal to 0, we have P is equal to P naught and rho as rho naught. This is nothing but atmospheric pressure, and this is the density of the gas at those particular conditions at sea level, mean sea level. Okay, so from this equation we can write P by rho power n is equal to P naught by rho naught power n. Okay, and if you differentiate this equation with altitude, that will be dP by dz is equal to minus rho g. Okay, in case of ideal gas, and in this case it will be minus dP by dz is equal to we'll go back and where is the equation? Yeah, using this equation, we'll use this equation. Okay, let's say equation, what was the number? Let's say this is equation, let's say this is equation 7, and equation 7, so we know dp by dz is equal to rho g for fluids. Okay, so if you use this relation, we'll be getting dz is equal to minus dp by rho g, and here if you do the same integration, differentiation here, you will be getting minus 1 by g into p naught power 1 by n by rho naught into p power 1 by n into dp, and if you simplify this, we'll be getting minus 1 by g into p naught by rho naught into p naught by p whole power 1 by n into differential p by p naught. Okay, and if you integrate this equation from z is equal to z naught, you will be getting z is equal to integral 0 to z dz is equal to 1 by g into n by n minus 1 p naught by rho naught into 1 minus p by p naught whole power n minus 1 by n. Okay, and now pressure as a function of altitude will be 1 minus n minus 1 by n into rho naught into g by p naught into z raised to the power n by n minus 1. Okay, and if you further simplify this, you will be getting, if you this is for pressure, right? So if we change it to density, so it will be the power will be changing. Okay, so this is of density and pressure changes with altitude. Okay, so along with this, temperature will also be changing, right, with altitude. So how do you account for that? So we can use ideal law, PV is equal to RT. So that means P by rho T will be equal to R. Okay, so this is in terms of volume and this is in terms of density. So similarly, from previous equations, if you change using this relation, we can write Tz by T naught is equal to 1 minus n by n into rho naught g by p naught into z. Okay, so you can also have a relation for dt by dz as well. So just differentiate this equation and you'll be getting this. Nothing but minus by n into g by r. Okay, and at the mean sea level, we generally accept P naught as 101.325 kilopascals and T naught as 288.15 Kelvin and rho naught of air as 1.225 kg per meter cube. These are standard atmospheric conditions at sea level. Okay, and let's say if the temperature could be assumed to be constant over the height change or the elevation, So we can write dP as minus P by RT into G into dz, or this can also be written as P naught to P dP by P, which is equal to minus G by R into 0 to Z dz by T. So if you integrate this, you will be getting P is equal to P naught into e power G Z by R T. This is only valid if temperature could be assumed constant over the elevation change. Then pressure can be written in this form. Okay. So these are different type of this is how pressure varies with height, temperature, and all other parameters. So, but how do you measure this particular quantities? How do you measure pressure in general? Like what are the devices that are used for measuring pressure? So we have many instruments for measuring pressure, for the measurement of pressure. So let's start with the basic one, that is open end manometer. Okay, so this is basically used to find the pressure of liquid is flowing in a pipe. Okay, so let's say you have a fluid which is flowing in a pipe and you want to measure pressure inside this particular pipe, or you want to measure the pressure of this fluid. So then you'll be using open end manometer, so where you'll be connecting this manometer to one end. So manometer generally has two ends, so one end of this manometer will be connected to the pipe and the other end will be open. So it will be of this shape, U shape. Okay, and this end will be connected to the pipeline, and inside this we have liquids depending upon our requirements. Sometimes we'll be using mercury. Okay, mostly we'll be using mercury. Okay, it will be filled with mercury, and whenever the water is flowing or liquid is flowing, it will be exerting the same pressure here, and depending upon the difference in the height levels. Okay, this mercury is filled inside this column, right? So depending upon this height difference of mercury in both the stems, will be calculating the pressure. So let's say if this difference is H, then this particular pressure will be equal to P is equal to rho G H2 minus H1, that is rho G H. So this is how we will be measuring pressure inside a pipe. And then we have differential manometer. So this differential manometer is used to measure pressure difference between 2 points. Okay, let's say you want to measure pressure across 2 different points. So we have a pipeline, very long cross section of pipeline. Let's say there are some bendings, there are some joints in this pipeline, and whenever there are some joints, obviously there will be pressure drop, right? So you want to measure pressure across these 2 points, P1 and P2. Then how do you measure? So that is by connecting a differential manometer. So here both the open ends will be connected to the pipeline. One end will be connected at point 1 and the other end will be connected to the point 2. Again, we'll be using mercury mostly, and depending upon this height difference again. So let's say this height difference is H. So P2 minus P1 or P1 minus P2 will be equal to rho G into H1 minus H2 or H2 minus H1. This will be giving us the pressure across 2 different points. And then we have seal and manometer. So this is similar to open end, but the only thing is that the other end of the manometer will be sealed or it will be completely closed. Okay. So if this particular manometer, closed end manometer, if it is exposed to the atmosphere, then this can be used as a barometer. Okay. If this end is open to the atmosphere, air will be exerting some pressure, right? So atmospheric pressure, that is basically atmospheric pressure, right? So this atmospheric pressure can be measured by calculating the height difference. Okay. So this Siglian manometer can be used as a barometer as well. Okay. Then we have inclined manometer. Inclined manometer. So inclined manometer is nothing but an open manometer, open end manometer or differential manometer, which is at a slight angle. Okay. So it will be at a angle. So why do we need to incline, or why do we need to place a manometer at inclination? Because whenever the manometer is placed at an inclination, what happens is that the accuracy of this manometer will be increasing. Okay. So let's say if you want to measure pressure in a pipeline, but the pressure exerted by this particular liquid or pressure exerted in this particular pipeline is very small. So in that case, you need an instrument which has a very high sensitivity. Okay, because you need to measure small values, right? So you need to have a device which will be able to measure this particular pressure with high accuracy or high sensitivity. So in that case, what we do is we'll be inclining this manometer so that we'll be able to measure the pressure with higher accuracy. Okay. And then we have micromanometers. Okay, this manometer is used for measuring very small pressure differences. Okay, and then we have elastic type pressure gauges. These are something which we'll be seeing in day-to-day life. Whenever you go for filling air in your cycle tube or bike tire, okay, you will be finding a meter there, right? That is a pressure meter actually. So that is a pressure gauge, and it will be measuring pressure of air inside this container. Okay, so that is basically elastic type pressure gauge. And then we also have electrical type, which is a transducer. Electric type pressure gauge. So whenever there is a pressure change, it will be taking it in terms of voltage difference, and then it will be processing the voltage difference, and then finally it will be giving us how much pressure is changing. Okay, so that is electric type pressure gauge. Okay, so let's see. Okay, let's try to solve one problem before going on to the next concept. So we have a connection, a pipeline connection. Okay, this is a bulb, and here we have another bulb. So let's say these dimensions are equal. Okay. So this is filled with water, and this is filled with oil. Okay, and we want to measure, let's say this is PW and this is PO. we want to measure PW minus PO. How do you measure it? So first of all, until this point it is filled with water and this part is filled with oil. Until this point is filled with oil, and again this is filled with what air, and in this region it is again filled with oil. Okay, so this is water, okay, and this is air. Okay, so what will be the value of Pw minus P naught? So how do you do it? So we have to take different points. So this is P1, okay, and then we have 2, 3, 4, 5, and this is 6. Okay, I will be giving dimensions as well. This is 8 centimeters, okay, and this is 4 centimeters, and this is 6 centimeters. Okay, so first let's calculate Pw minus P2. So what will be the value of Pw minus P2? That will be rho, that will be rho GW into Z1 minus Z2. Okay, so pressure will be same in this until this point, because this is a horizontal strip, right? So if two points are at same height and if the fluid is continuous, then they should be at the same pressure, right? So here Pw and P1 will be of same pressure. So what will be the difference between P? So this is also Pw, okay? So now Pw minus P2 will be equal to what is the density of water? 1 into, let it be so this is rho W into G. Let it be G, and what is the height difference? Z1 minus Z2, that is 4 centimeters, right? Into 4. Okay. This is Pw minus P2. So now we have to calculate P2 minus P3. So again, let's use the same principle. So they are at same height, and this is a continuous liquid. Okay, that means the same liquid is present. So obviously they should be at same pressure. So that means P2 minus P3 will be 0. Okay, so now P3 minus P4. Okay, what will be the height? Again, it will be rho O, is oil, into G into Z3 minus Z4. Okay, so this will give us density of oil. I haven't given, right? Let's say density of oil is 0.86. Okay, so density of oil is 0.86 into, let it be as G, and what is the height difference? It will be, so this direction we are taking positive, right? So this will be negative, okay, because here we took it as positive. So this will be minus 12. Okay, so what will be the value? Just simplify it and tell me the final value. So now we need to calculate P4 minus P5. Okay, so again they are at same height. Okay, okay, so they are at same height, and the connecting liquid is the same liquid, so obviously it should be 0, like P4 minus P5 will be 0, P4 minus P5 will be 0, and now P5 minus P oil, this will be rho O into G into Z5 minus Z6. Okay, so this will give us 0.86 into G into, this will be positive again, that is 6. So what will be the final value? So if you add all these values, then you will be getting PW minus PO. So it should be giving you the final answer. So this is how you calculate pressure difference across two different points. Okay. So now coming to the next concept is water pressure acting on a bank or gate. So when you're designing a dam gate, okay, or let's say we already have a dam gate. This is theta angle. So when you're storing water, there will be pressure acting on this dam wall, right? So it will be acting perpendicular to the dam surface, right? Okay. So if the total pressure due to water pressure acting on the bank built at the angle of theta, so these are the total pressures. Okay. Then total pressure dP acting on a minute area, let's take it as dA. Let's take dP as a total pressure acting on a small area of area dA. Okay, so let's say this is a centroid. Okay, and its y coordinate is, or y coordinate is, this is the y axis and this is the x axis. So the y coordinate, let's say it is y naught, or let's say it is yg. Okay, and so this is yg, and the height will be, or the depth will be hg. So the total force Ft equals the product of pressure at the centroid and the water area of the bank wall, right? So let's say if initially we'll calculate dF, that is dF is equal to rho g into h into dA, so which is acting on a small area. Okay, so this will be equal to rho g into, if you convert it into y coordinates, it will be y into sine theta. Okay, now total force acting on this wall or dam gate will be Ft is equal to integral dF over the entire area. So that will be rho g into sine theta into integral y dA. So now total force acting on this bank will be Ft is equal to rho g into sine theta into yg into area, which is equal to Okay, so force Ft will be equal to rho g into sine theta into yg into total area, that is A, and this can also be written as rho g into hg into A. Okay, so this is how you will be able to calculate the total pressure acting on a bank of a dam. Okay, and it is also important to calculate the center of pressure as well. Okay, so center of pressure is nothing but a point at which, so like there are different forces acting on the wall, right? So let's say like there will be different number of forces, there are different number of forces which are acting on the wall, right? So if you club them into one force and apply at a particular point, it should be causing the same turning effect around the, or it should be causing the same moment around the turning axis. Okay, so this is going to be the point center of pressure. This particular point will be the center of pressure. So it is nothing but the point of P at which a single force, that is P, produces a momentum equal to the total sum of the moments around the turning axis of a gate. Okay, so you need to understand this center of pressure as well. Okay, it is already explained. And coming to pressure on the floating bodies. Okay, this is one more important concept. So let's say a body is immersed in water or any liquid, so maybe. So let's say the density of body is, okay, so yeah, this is the surface of water, right? So at surface we know atmospheric pressure will be acting, that is P naught, and let's say this is height h1. Okay, this is height h1 and this is h, that is side of the body, and this is h2. Okay, so this side also there will be some pressures or forces acting. Okay, and from bottom there will be some forces acting on the body, and from the top there will be some forces acting on the body. Okay, so now if you equate them, so we know like they are at the same level, right? So horizontal forces, all the horizontal forces will get cancelled out, but whereas vertical forces needs to be balanced. So let's say from the lower part F1 is a force acting, and from the top section F2 is a force acting. So F1 will be equal to P naught plus, P naught is the atmospheric pressure, we need to consider that as well, P naught plus rho into G into H2, that is height or depth of this liquid, H2 into its area of the body, and F2 is going to be P naught plus rho G H1 into A, that is the force acting from the top direction. Okay, so now the resultant force will be F is equal to F1 minus F2. So this will be equal to rho G into, because this gets cancelled out, right? Area is same, so P naught gets cancelled out, so we'll be left with rho G into H2 minus H1 into area. So this can also be written as rho G H into area. So again, H into area can be written as volume. This will be rho G into volume. Okay, so this is how you will be calculating resultant forces acting on floating bodies. So let's say this is a completely immersed body, right? Let's say if the body is not completely immersed and it is somewhat floating in the liquid, okay, something like this. So in this case, how do you measure? So simple, again we will be having atmospheric pressure, that is P naught, and from bottom we will be having P naught plus rho G H, which is the depth. Okay, and again all the horizontal forces they'll be cancelled out because they'll be equal, and now the resultant force, the F, will be equal to F2 minus F1, so that will be P naught plus rho G H minus P naught. This gets cancelled out and we'll be left with rho G H. Okay, so this concept, that is pressure on floating bodies, is nothing but Archimedes principle. You must have heard about famous Archimedes law, right? So that is the buoyancy experienced by liquids. Okay, the body in a liquid experiences a buoyancy force equal to the weight of the body, weight of the liquid displaced by the body. This is known as Archimedes principle. Okay. And when bodies are floating on the liquids, they will be coming across two terms, that is center of buoyancy and center of gravity. Okay, so that is also important. So this is particularly important in design of ships. Okay, so whenever ships are going in water, or like whenever they are sailing in water, uh, they come across different waves, right? So especially in oceans, when vessels are traveling, vessels of cargoes are when they are traveling in oceans, they come across very high tides, right? So in that case, what happens? The ship body will be tilting from one direction, one side to the other side, right? So in this case, it is important to understand the stability of floating body. Okay, how these ships remain in the place. Okay, let's say this is a body of the ship which is floating. So this is at an inclination. Okay, I think it's not clear. So let me write. So let's say this is the inclination. So because of some tide, the boat was moving from one side to the other side. So boat has center of gravity and center of buoyancy as well, right? So let's say G is, let's say we have two terms, GC, and this is M. Okay. So whenever be it any body, not on a ship, whenever a body of weight W is floating in a water with some inclination, so what happens is that center of gravity or centroid does not change with the inclination of the body; it remains same. But whereas center of buoyancy, that is C, will be changing to a new location, that is C naught, C dash. Okay. So whenever the center of buoyancy is shifting, obviously there will be some forces which are acting on the body. So let's say a couple of forces, that is Ws or Fs, they are acting on this ship. Like the couple is nothing but two forces, right? So couple is acting on this ship. So one will be the weight of the body, that is W, and the other one is force, that is acting in the upward direction. Okay. So that will be produced and it will be trying to restore the ship position to its stability. Okay. So these forces are nothing but restoring forces, and this new center of buoyancy will be passing. If you connect if you connect the center of center line of the body with the new center of buoyancy, it will be passing through a point M. Okay. So okay, this center line is called metacenter. Okay, and this point GM will be called metacentric height. Metacentric height. Okay, so this will be passing through point M. Okay, there is a significance for this. If point and if you observe, if the body, if the ship or the body tilts more in this direction, this C will be shifting outward direction, right? So if this is shifting in the outward direction, what happens is that this point M will be moving closer to point G. Okay, and after at a certain time, this M will be moving below G. Okay, so there are two cases. One, M is above G, and the other one is M below G. Okay, so if M is above G, then the restoring forces will act to stabilize the body. Okay, so the restoring force will act to stabilize the body to bring back this into the original position. But if at all this M comes below G, then the coupled forces will act to increase the roll of the ship and it makes the ship unstable. Okay, so you have to make sure that M is always above G. Okay, this is how the bodies or the ships get stabilized on ocean surface. Okay, and coming to height GM, that is metacentric height. This metacentric height, this plays a very important role. Okay, so metacentric height, there are some standards as well for merchant ships, particularly liners. This GM should be from 3 to 1 meter. Okay, this is for merchant ships, and for sailing ships, this is from 0.4 to 1.25 meters. Okay, and for battleships, this is from 1 to 1.5 meters, and for river raft, this is all the way up to 3.6 meters. So metacentric height, that is nothing but GM, right? So this will be equal to CM plus CG. Okay. And coming to fluid statics when containers are moving. So until now we were only discussing about bodies when they're at rest, right? But they will be coming across situations where bodies are moving as well, right? So let's say a vessel, there's a vessel which is having water inside the vessel. Okay, vessel is carrying liquid. Okay, and this is in motion. This is moving in a straight line, or let's say there will be also cases where this is rotating. Okay. Uh, if there is no relative flow of liquid while the vessel and liquid are while the liquid and vessel move as a single body, so in these cases we will see what are the pressures acting and how do we calculate them. Okay, so this can be treated as mechanics of a stationary state. Okay, first let's see in case of accelerated in a straight line motion. Okay. Yeah. So whenever a body is moving in a straight line with an acceleration A, so obviously liquid will be moving in the backward direction, right? Uh, let's say m is a mass of, let's consider sample. Let's say this mass is around m. Okay, so if the body is moving in this direction, it will be experiencing a force in this direction, that is ma into x, and weight of the and there will be also a force acting in this direction. Okay, so weight of the sample will be mg in down direction, and there will be a force which is acting. Resultant of these two forces, max and mgx, will be in this direction, that is f. Okay. So these 2 points is P2 and P1. These are two different points in the same liquid, right? So again, P2 minus P1 should be equal to 0. But at the same time, there are also two different forces which are acting here, right? So we need to consider them as well. So P2 minus P1 is also equal to minus rho into Ax into x2 minus x1 minus rho into Az plus G into Z2 minus Z1. Okay, this again, if you consider these two equations 1 and 2, it should be equal to 0. Then if you resolve everything, you will be getting tan theta is equal to Z2 minus Z1 by x2 minus x1, that is equal to Ax by G. Okay, so this is a theta. Okay, this is how you can resolve forces when the body is moving in a straight line. And there is also a case where body is moving accelerated in the vertical direction. So when it is moving in the upward direction, what happens? Let's consider liquid stream or mass of a liquid which is moving in the upward direction with Ax acceleration. Okay, weight will be acting in a downward direction. Okay. Now to balance out the forces, so let's say the force is acting in the upward direction. Okay, net resultant force. So this net resultant force will be minus F minus W. W is the weight of the sample. Will be equal to m into Ax, right? Okay. So now F is nothing but the pressure into its area, differential area, minus what will be the weight of the sample? Let's say rho into h into its area, let's say dA into gravity. This should be equal to, again, mass is rho into h into dA into g by g, because we want to calculate mass, right? It will be by gravity, weight by gravity, into a x or az. Let it be az. Okay, it's moving in upward direction. It will be az. So now for vertically downward direction, or let's simplify this first. Now P will be equal to rho g h plus rho g h az by z. Now if you simplify this, you will get to rho g h into 1 plus az by g. Okay, and similarly for vertically downward direction, vertically downward force, P will be equal to rho g h minus rho g h into az by g. This is nothing but rho g h into 1 minus az by g. Okay, and if the sample or if the liquid is moving in an inclined motion, okay, accelerating in an inclined motion. So let's say this is inclination of theta, and if this wagon or container is moving, so the liquid will be at an angle. This is going to be theta. Okay, so now in this case it is moving with the acceleration a. So you have to just resolve the forces. We will be having F sin theta is equal to ma, that is in this direction, and we have a weight component F cos theta minus mg is equal to m a z. This is in x direction and this is in z direction. It will be moving in the y direction as well, right? Because it will be moving in terms of altitude as well, right? So we have to consider that as well. So that will be m into az. Okay, so now if you divide them, you will be getting tan theta is equal to ax by g plus az, which will be slope of the free surface. Okay, so similarly, if it is moving in a downward direction, tan theta will be equal to minus ax by g plus minus az. Okay, so, and in case of rotational, okay, if there is a rotational flow or rotational motion, say if the liquid is moving or rotating with the angular velocity omega, this is height z. Okay, if it is moving at a constant angular velocity of omega, okay, and let's say if phi is the angle formed by the free surface and the horizontal direction, then tan phi will be equal to mr omega square by mg, that will be r omega square by g, and also tan phi will be dz by dr as well. Okay, so that means dz will be by dr will be equal to, I'm not going into this derivation part. Okay, r omega by g. So you will be coming across this particular derivation in your mechanical operations, so I'm not going too deep into this, so I'm just writing down the equation. So if you integrate this from z is equal to h naught at r is equal to 0 to z is you will be getting c is equal to h naught, and after integration z will be equal to r square omega square by 2g plus c. So if you apply this condition, you will be getting c as h naught. Okay, and if you substitute it here, you will be getting z minus h naught is equal to r square omega square by 2g. Okay, so now P2 minus P1 will be, that is pressure difference will be rho omega square by 2 into R2 square minus R1 square. Okay. So coming to questions part, if you have any doubts, you can ask me, or you can unmute yourself and ask me, or you can post them in the chat box as well. If you don't have any doubts, then we can move on to the problem session. We'll move on to solve the problems. You can either unmute yourself and ask me, or you can post them in the chat box as well. Any doubts? Okay, we'll move on to the problem session. Coming to the first question, the stresses associated with static fluid are shear stress, thermal stress, normal stress, all the above. So when you're talking about static liquid, what are the stresses that are involved? So it is going to be, there will be no other stresses, right, like shear stress or thermal stress. It will only be having normal stresses, and this is also called as pressure, right? It will be option C. Coming to the second question, absolute pressure is defined as atmospheric pressure, gauge pressure. Absolute pressure is defined as absolute atmospheric pressure plus gauge pressure. Atmospheric minus gauge, no relationship, none of the above. So atmospheric absolute pressure is measured from the vacuum, right? So it will be atmospheric pressure plus the gauge pressure, right? It will be option A. So coming to third question, hydraulic press employs the direct application of Bernoulli's principle, Navier-Stokes principle, Pascal's law, Archimedes principle. So which principle will be used in hydraulic press? It is Pascal's law, option C. Coming to fourth question, the pressure in a homogeneous liquid at rest is the same at all points throughout the liquid, depending on the direction, the same at all points at the same level, dependent on this density. So which factors influences the pressure in a homogeneous liquid at rest? Like which of these following will be correct for a homogeneous liquid at rest? So pressure will be same at all points at same level, right? This is option C. A large open tank contains a homogeneous fluid at rest. Which of the following is not true regarding pressure at upper surface of the fluid? It is the same at all points at that level. It will increase if the density of the fluid increases. It will increase if the atmospheric pressure is increased. All statements are true. So we are asked to find out the wrong statement, right? So at the top surface or the upper surface, only atmospheric pressure will be acting, right? So, and also it will be same at all the points at same level. Okay, so option A is correct. So it will increase if the density of the fluid is increases. So this doesn't have anything to do with the density of the fluid, right? Because this is atmospheric pressure. So even if you change the density of this fluid, there is nothing. Then nothing is going to be changed in the atmospheric pressure, right? So this is wrong answer. And the third option is it will increase if the atmospheric pressure is increased. So this is true because if the atmospheric pressure itself is changed, then obviously this pressure will also be changed, right? And all statements are true. This is again wrong. These all statements are not true. So it will be option B and C, but here we will only use B because that is the wrong statement, right? So option B and D both are correct in this case. Okay, this is also correct. Which of the following is based on perfect vacuum? So when you are measuring a pressure with respect to the perfect vacuum, then that is going to be called as absolute pressure, right? Okay, and atmospheric pressure is going to be the pressure exerted by the atmosphere at standard temperature. Okay, that is atmospheric pressure, and gauge pressure will be the pressure which is measured with respect to the atmospheric pressure, right? So that is gauge pressure. Okay, and this is going to be the absolute pressure. Okay, what is the value of standard atmospheric pressure among the following options? For 14.7 psi, word 1.5 pascals, 750 mmHg, all the above. Which of them is a standard atmospheric pressure value? Standard atmospheric is 1 atmosphere, which is nothing but 101.3 kilopascals, or 101.3 into 10 power 5 pascals. This should also be equal to 14.7 psi, and this is also equal to 760 mmHg. Okay, so which of the following is true? It will be option A. Okay, so which of the following functions as a barometer? Open-end manometer, inclined manometer, sealed-end manometer, micrometer. So we have already discussed this. So sealed-end manometer is going to be worked as barometer. According to Archimedes' principle, the buoyant forces experienced by a fully or partially submerged body in a fluid is equal to dash of the fluid displaced by the body. So we just discussed this now, right? So it is going to be the, so is it volume, mass, weight or pressure? It is going to be weight of the displaced body, displaced fluid. Okay, so if you have any doubts, you can ask me, or you can either unmute yourself and ask me, or post them in the chat box as well. So if you don't have any doubts, we can end this session. Any doubts? Okay, so if you don't have any doubts, then we can end this session. Thank you everyone. Thank you for attending the session. Let's meet on next Tuesday, same timing 6 to 8 p.m. Okay. Thank you everyone. Thank you for attending the session.